Today, Simon, Alex, and I will be covering Problem B, spinning a wheel. We were asked to model the motion of a cockatoo making a full rotation around a bicycle wheel as seen in a popular video. The bird, initially perched on top of the wheel, had some freedom of movement in both the tangential and radial directions. In order to model this phenomenon, we have to make a few initial assumptions to simplify our calculations. We first assume that reaction forces caused by movement of the bird on the wheel are negligible. We also say that the bird's exerted energy is self-contained and the air resistance is negligible. Because our calculations are in polar coordinates, we presume that the tangential component of the bird's movement is along the wheel. Finally, we assume that the bird's mass is concentrated in one point. To start our derivation, we establish multiple constants used, including acceleration due to gravity, the mass of the bird in kilograms, the radius of the wheel in meters, the wheel's moment of inertia in kilogram meters squared, and the magnitude of the frictional torque in Newton meters. Our derivation also involves multiple inputs, including r of t, which is the radial distance of the bird from the wheel rim over time, and lowercase theta of t, which is the angle deviation of the bird from its anchor point. These two input functions must be bounded due to the bird's physical limitations. Our output is cap theta of t, the angular position of the anchor point on the wheel, with our reference being at the top of the wheel. To actually derive our formula of motion, we need to start with a free body diagram. We find that the force of gravity always acts at an angle of cap theta plus little theta from the wheel center. Notice that the only torque acting on the wheel is the tangential component of the force due to gravity, F sub x. Our first goal is to find the total torque, which must start with finding tangential forces. Our F sub x is the force of gravity times the angle made with the starting position at the top. The torque of the bird on the wheel is the tangential force component times the total radius, which is equal to this expression. We also want to consider one other torque, the resistant torque of the friction force. Since this resistant torque is in the opposite direction of the angular velocity, we use this in formula to ensure it. Our total torque will be the torque of the bird plus the resistant torque, which is equal to this expression. In order to find the total moment of inertia for our system, we establish the wheel's inertia first. Remember that the bird's the point mass, so its moment of inertia is the mass times the total radius squared, giving us a total moment of inertia expression here. Combining everything together, we use Newton's second law for rotation, which gives us this formula for angular acceleration. Plugging our total torque and inertia in, we are given our formula. Sadly, this differential equation cannot be solved analytically.
In order to analyze this ODE, we need to use numerical methods. Right now, our ODE is in the form y double prime equals a function of y, y prime, and t. Let's simplify it by letting u equal y prime. That results in a system of first-order ODEs. We can use those first-order ODEs to modify Euler's method, giving us the following algorithm. If we have a t0, y0, u0, and t1, we can find the next y value using u0 as the slope, and the next u value using the function f as the slope. Before we go any further, we need to make some simplifications. Since the change in theta has no impact on the system's moment of inertia, and angular momentum must be conserved, theta will not be able to increase the energy of the system or keep the wheel spinning. Therefore, for our purposes, theta will be equal to 0. Since the entire ODE outside of r and theta is only dependent on cap theta, we will also assume that r is only dependent on cap theta, and that it is periodic. Because of our limited time, we will restrict r to the following family of functions: sinusoids. In order to test this algorithm, let's choose some constants that will approximate the wheel and the bird in the video. We also need a value for r. This time we'll just let it equal a constant. These are our initial values for cap theta and cap theta prime. Since cap theta is 0.2 and cap theta prime is 0, that means that we would be releasing the bird at a near vertical position. Now, let's simulate it. In order to simulate the solution to our initial value problem, I wrote a Python script. This Python script uses the modified Euler's method I described earlier to estimate the solution. It calculates 10,000 steps over the interval 0 to 10. Let's run it. Alright, so here it gives us a graph. On the vertical axis, we have values for cap theta and revolutions. 0 is the top of the wheel. Here we can see that the bird starts near the top and then begins to fall, and then it goes back up, but not far enough to get over the top of the wheel, which is represented by this vertical line. Since the bird didn't make it over the top that time, let's choose a new function for r. In this case, the bird's center of mass will move the farthest away from the wheel when it is at the top, or when cap theta equals 0. Let's simulate it. Alright, here's the graph. As we can see, the bird still didn't reach the top. Let's also give it a little push. This time we'll start at the top with an initial angular velocity of 1. Alright, that's more like it. Here we can see that the wheel rotates once, twice, and almost 3 times, but it doesn't quite make it to the top, and then it falls back down. We're still not getting the behavior that we want. In order to gain a better understanding of the system, we need to test a range of values. Recall our form for the function of r. Since the bird has a limited range of motion, a and b won't be able to change that much, so for our purposes we'll keep those values constant. However, we'll test a range of values for omega in 0.1 to 2.1 and phi in 0 to 2 pi. We need a metric in order to compare these simulations. For each simulation, we will take the slope of the best fit line over the interval 0 to 50 with cap theta starting at 0 and cap theta prime starting at 1. If the slope is above 1, we can be pretty confident that the bird continued to spin for the entire duration of the interval. Let's simulate it. Alright, here's our graph. On this axis we have omega plotted, on this axis we have phi, and then on this axis, the vertical axis, we have the best fit slope of each simulation. If we look at the points, we can see that most of them are hovering around 0. However, there's a thin slice here at omega equals 1 that, if we look at it from the phi side, it looks kind of like a sine wave. Let's take a closer look at the simulations where omega equals 1. Phi will still be in the interval 0 to 2 pi. Alright, here's our graph. If we look at our points, it looks like we're getting the behavior we want at around phi equals 3. Let's use a best fit sine wave to find which phi maximizes this effect. Here's the equation of our best fit sine wave. Let's find the phi that maximizes the best fit slope. If we assume the value inside the sine should be equal to negative pi over 2, note the negative coefficient on the sine, then we would get phi equals pi. Therefore, the optimal function for r, given our assumptions, is equal to 0.07 plus 0.05 times the sine of cap theta plus pi. Here's a graphic depicting the optimal solution for r. The dotted line shows the path of the bird's center of mass as the wheel rotates counterclockwise. What initial conditions are necessary for this to work? Let's simulate cap theta with the optimal function for r in the following range of initial conditions. Cap theta naught is between 0 and 2 pi, and cap theta prime naught is between 0 and 10. Here's our graph. On this axis, we have theta naught. 0 and 2 pi here are the top of the wheel, and pi here in the middle is the bottom of the wheel. On this axis, we have theta prime naught. If we look at the points, we can see there's a pretty stark difference between the initial values that worked and the initial values that didn't. If cap theta doesn't equal 0 or 2 pi, cap theta prime has to compensate for the lost energy. According to our model, the bird would not have been able to rotate the wheel if it started at rest on the bottom of the wheel. Is there a maximum speed? Yes, we simulated the system with various parameters over the intervals 0 to 500 and 0 to 1000, and there appeared to be a maximum speed. However, we were unable to find it. There are too many inconsistencies in our simulations at that scale to make any meaningful conclusions.
After finishing the mathematical and numerical computations on the wheel, we desired to also test our equations for movement experimentally with a real wheel and real moving mass. The goal here was to create a wheel that could replicate the desired vertical motion of the bird from the video, a wheel where we could program in our function for R. To do so, various parts were needed, including a linear actuator and some way to control it, an accelerometer, a microcontroller, power sources, and an actual wheel that could hold all of these components. The first step in the wheel design was its circuit, consisting of an Arduino Nano, ADXL345 accelerometer, L298N H-bridge, dual 6V and 9V power supplies, and a motor needed for the construction of the linear actuator. Next came the mechanical components, all of which had to be 3D modeled in order to fit the unique requirements of the individual components being used. They were then 3D printed and assembled. After soldering all of the components together and attaching them to the wheel, the final product was completely assembled. While all of the electronic pieces worked as intended, such as the accelerometer, shown here, a plague of mechanical issues and breakages within the linear actuator ended up preventing an actual test of the wheel. This means that while we were close, in the end, we were not able to see if our mathematical results would be experimentally replicable. Overall, we are proud of the model that we created, but optimizations could be made. First of all, we could have considered a number of additional components of force, such as air resistance and acceleration of the bird. The bird's acceleration could be modeled in two different ways, constant acceleration and variable acceleration. Also, the resistant torque could have been more accurately modeled with a component proportional to angular velocity as well as a constant component. Assuming that the bird is not a point mass could have also more accurately given us the moment of inertia of the bird through integration and allow for better calculation of air resistance. These improvements would allow us to then consider theta of t in our numerical analysis. In the future, we hope to find a formula that can be solved analytically without loss of accuracy. In terms of numerical analysis, we could also consider other periodic functions, such as the one shown here. And while we fleshed out the physics and numerical analysis, given more time, we could complete a finished physical model to model the equations that we calculated earlier. Here are references, and thank you for watching.